This is the video to introduce the credentials and proofs of certificates, which is one of the components of the MEDINA framework. The video is organized in 4 different parts. First, an overview of the tool. Then, I will show how to use it, including a quick demonstration. Next, we will dedicate some minutes to the installation of the tool. And finally, some pointers for further reading about MEDINA. Let's start with the introduction. To put in context, MEDINA project aims to provide a framework of tools and techniques supporting the continuous audit-based certification of cloud services in the UK standard. The credentials and proofs of certificates is one of the many tools developed in MEDINA for making the audit-based certification more secure and trustworthy. First of all, it is important to introduce what self-sovereign identity technology is. It is a recent way of managing digital identities in which individuals or organizations have total control over their personal identity, which is only owned by themselves. Digital identities are created through verifiable credentials, which are tamper-evident credentials whose authorship can be securely and cryptographically verified. If any part of the identity needs to be probed, verifiable proofs based on the verifiable credentials are generated. These proofs are also cryptographically signed and can be securely verified. Once the concept of self-sovereign identity is clear, let's introduce the MEDINA Self-Sovereign Identity Framework, which is the component in MEDINA which provides credentials and proofs of certificates. In the slide you can see the 3 actors involved in a generic self-sovereign identity architecture, particularized to MEDINA. First of all, we have the issuer, which issues verifiable credentials, making and securely signing claims about an individual or organization. In MEDINA, the issuer is the Certification Authority Board, the CAB. The CAB will receive input from the MEDINA framework. Then, we have the owner. In MEDINA, each cloud service provider will be a self-sovereign identity owner, which owns verifiable credentials received from the CAB. Next, we have the verifier, which makes proofs request and receives proof responses from the owners. The proofs response are verified to validate the signatures. This role will be covered by the cloud service provider's clients. The self-sovereign identity framework is backboned by a blockchain network which provides secure storage of signatures to be able to securely verify them. Here you can see the 3 main self-sovereign identity components in detail. The issuer, which provides the Certification Authority Board a way to generate and sign verifiable credentials about security certificates related to cloud service providers, which are the second component. The owner, which consider the security certificates as part of their own identity. Finally, we have the verifier, providing a way for cloud service providers' customers or clients to ask and verify proofs of the security certificates. For providing these functionalities, the MEDINA Self-Sovereign Identity Framework has the following features. 1. It provides a user-friendly graphical interface for improving usability. 2. The tool provides security by design thanks to the use of blockchain as backbone. Integrity and transparency are guaranteed for the signatures. 3. The cloud service providers operate in an automatic way. It makes the use of the tool easier for them. 4. The tool exposes a REST API for an easy provision and retrieval of information. By this way, self-sovereign identity technology is transparent for the users. 5. Finally, the tool has been implemented in a way that it is easy to be extended in terms of information related to the security certificates. This is how the self-sovereign identity system fits inside the MEDINA architecture. As explained, there are 3 components. The issuer, which receives input from MEDINA Automated Lifecycle Manager about the security certificate status. The Certification Authority Board, as an actor, will manually issue the credentials automatically filled with the information received from the rest of the MEDINA framework. The issuer emits verifiable credentials to the owner, the cloud service provider itself, which locally stores the credentials that can be listed by the compliance manager or auditors. Finally, the verified, which is used by cloud service provider customers to make proof requests and receive proof responses from the owners. Well, here you can see a summary of the list of components and actors the self-sovereign identity framework interacts with. The lifecycle manager, in the case of components, and in the case of actors, the Certification Authority Board for the issuer, the compliance manager or the auditor for the owner, the cloud service provider customer for the verifier. Now, Let's enter in more detail in how this component can be used. The first component in the issuer is the API we have developed for receiving security certificates features from the Lifecycle Manager. Here you can see the swagger of this API, allowing the creation, update, removal and listing of the security certificates. Once the security certificates updates are received by the issuer, or the Certification Authority Board, can create and sign a security certification for a cloud service provider through the issuance of a verifiable credential. Let's see a quick demo about this certificate issuance functionality executed by the issuer.
Okay, let's start with the self-sovereign identity demo. First of all, I would like to introduce you on the different self-sovereign identity framework components we have in MEDINA. The first one is the Certiificates API. This is the API the issuer exposes for receiving the security certificates information updates from the Lifecycle Manager in MEDINA. Here you have the different endpoints. Then we will have the issuer instance that will be deployed in this case in Tecnalia for validation purposes. The next component is the holder or owner component that will be part of the cloud service provider instance from the MEDINA framework because it has been integrated in the integrated UI of MEDINA. And finally, we will have also a verifier instance also deployed in Tecnalia for validation purposes. Okay, let's start now with the demo itself. Well, the first step is to list the pending certificate updates to be issued by the issuer itself. For this purpose, we will use this endpoint, and here we have the list of pending certificate updates. We only have one pending certificate update at this moment. Well, if we go to the issuer instance, the first step is to connect to the issuer instance itself and go to the Certificate Credentials tab. Here we have a button to create a new credential. Let's do that. And here we have the information we need to fill to emit a new credential. The first information is the connection. We need to indicate who will be the owner or the holder of the emitted credential. In this case, it will be a Tecnalia holder in the text environment. Here we have to indicate the schema of the credential we are going to emit. This is the one of the final version of the MEDINA Self-Sovereign Identity Framework, but well, as you can see, we have many. And then we have to complete the attributes with the values to be included inside the credential. We have to complete the cloud service ID and the certificate status. And as you can see, the information is already filled. It's automatically filled by the Self-Sovereign Identity Framework. And what is this information? This information is the same we have received in the API. Look, we have the certificate status suspended, and this is the cloud service ID. If we come back to the certificates API, we can see that the information is the one that was still pending. So when the information has been filled, we only have to to push the accept button, and the credential should have been emitted correctly to the owner.
Once the certificate has been issued by the Certification Authority Board, it is automatically received and locally stored by the cloud service provider. At any time, the owner can list the received security certificate's verifiable credentials. Let's see now how the cloud service provider or the owner can list the received credentials.
Okay, once the credential has been emitted by the issuer, we can check if the owner, the holder, the cloud service provider has correctly received this credential. For this purpose, we go to the integrated UI in which we have the owner or holder component of the self-sovereign identity framework. We need authentication. Let's use this user, for example. And if we go to the credentials and proofs of certificates, we will see the different options for the owner component. In this case, if we go to the certificate credentials, we will see the list of received credentials from the issuer. In this case, this is the only credential we have, in which the cloud service ID is this one and the certificate status is suspended. And this is the credential we have just emitted from the issuer.
The next step in the flow is for a cloud service provider customer to ask for a proof of a specific security certificate status. For this purpose, a proof request is defined by the verifier and sent to the cloud service provider. Let's see a demo of this process.
Okay, once we see that the certificate has been correctly received from the issuer in the owner, we can start with the demo of the proof request from a potential cloud service provider customer. For this purpose, let's go to the verifier instance, and the first step, as before with the issuer, is to connect to the verifier and make a proof request. For this purpose step of using the certificate credentials tab, we will go to the certificate proofs tab. And we have here the request proof button we will use for this purpose. Here we have the information we need to fill for the proof request, and the first one is the connection. In this case, we are also going to use the technical holder test. Here we can include some comment to identify the proof. Proof 1 at the date will be included for the demo and with the time. And here we have the list of attributes we are interested in. This is the suggestion of the attributes following the schema or the final schema we use in Medina, and let's request both attributes. And here we have a final section related to conditions that it is not suitable with the current schema, but it will be available in future extensions of the self-sovereign identity framework, in which we can make zero knowledge proof. Zero knowledge proof allow the holder to prove some numeric conditions without revealing the current value. For instance, the most typical example is the age. I can prove that I am older than 18 years without telling you my specific age. This is the idea behind the conditions section and the zero knowledge proof used for this section. However, with the current self-sovereign identity schema, we don't have any numeric value, so this is not suitable in this case, but the tool is prepared for future extensions using the zero knowledge proof. So, well, we have the connection, we have a comment, and we have defined the attributes we are interested in. Let's make the request, just accepting with the button.
Finally, when the proof request is received in the cloud service provider, it automatically answers accordingly, and sends the proof response to the verifier. This proof response is received and verified against blockchain for security reasons. Let's see the demo of this final process then.
Once the proof request has been made by the verifier, we will see the request we have just done in the verifier, and the request has been sent. If we come back to the holder and we go to the certificate proofs tab, we will see also the request just received from the verifier. In this request, we will see the information we have automatically answered from the owner. Why automatically? Because we have configured the cloud service provider owner component to respond automatically to the different requests made from different verifiers. And in this case, the certificate proof request has been indicated as done because the answer has been already sent to the verifier. Let's see this again on the verifier. Let's update the information, and now the certificate proof is indicated as done. Here we have the value of the attributes we have request from the holder, and the proof appears as verified because it has been verified against the blockchain network. So this is the final process on the complete self-sovereign identity framework flow.
Next, we will give some technical details about the component and explain how to install it. As we know, there are three components in the self-sovereign identity framework. In MEDINA, the issuer and the verifier are provided as a service from Technalia infrastructure. Only the owner needs to be locally deployed at the different cloud service provider premises. It is a Docker image that needs to be run locally. Here, you can see the steps that need to be followed for pull and run the Docker image from the MEDINA artifact. An account is needed in advance as login is required. If you follow these steps, the blockchain will be accessible at the indicated URL. Here you can see a list of technologies that have been used within the MEDINA self-sovereign identity framework. Hyperledger Indy and Hyperledger Aries are the selected self-sovereign identity technologies for the blockchain network and the backend implementation respectively. The frontend including the graphical interface of the three actors has been developed in React. The API in the issuer for receiving information from the Lifecycle Manager is implemented in Python. Finally, Docker has been considered for easy installation. This is all about the self-sovereign identity framework. However, if you are still interested in more details about this component, or about MEDINA in general, here you have some interesting pointers. If you need more details about the component presented so far, or about the MEDINA project in general, you can visit the official webpage on the first link, where you will also find all public deliverables of the project. Project-related videos, such as demos or training videos, are also available in the MEDINA YouTube channel. The third link points to the MEDINA community in Zenodo, where among other things, the papers produced during the project are available. Finally, the source code of the project is available at the last link, in the MEDINA GitLab. And that was it. Thank you and goodbye.